So, welcome back. And after what we have done in kinematics, where the only two dimensions, length and time, were considered, we introduced many things. Now, we need to study what is called the cause of motion. Yani, the laws of motion, wherein we will study many factors. Okay. In the first instance, and generally, what we'll do is we'll try to understand very deeply as to what is a force. And then there are many forces. I've told you before, I've used that term many a time without discussing it, relying that your knowledge of the high school class will be able to make you conversant with the concept of the force, which is of course a vector quantity, just like acceleration, velocity and displacement, etc., which I have introduced in the vector quantities beforehand. And then if like I said in the case of vectors, that if two vectors of the same variety coexist, then there is a resultant vector. So similarly, if on a body many forces are acting, then they can be added according to the vector laws of addition, the protocol that we use for that. And the net force, because of a large number of forces acting in a body, that will be equal to, that will be of some magnitude and in some direction. So sometimes the resultant force is equal to 0. That means a set of forces balance out each other, and the net force on the system will be equal to 0. We'll discuss those in details. Then there is, if the resultant force is not 0 and a single force resultant is working on a body, then that force is called an unbalanced force. We'll return to these things in detail as we go ahead. Now, in the course of our discussion the other day, in the last lecture, I mentioned Galileo, a person from Europe who used to live in what is nowadays modern Italy. Galileo, as I told you, and I'll discuss the concept of the force that used to be there since millennia, and finally in the course of the establishment of the great universities, particularly those in the Middle East and in, for example, Qartaba and Baghdad and many other places, there were universities where people from all over the world used to come and study science and make discussions and contribute to the progress of science. So Galileo, he gave a law which we call Galileo's law of inertia. Okay, and that states, as you know from the high school classes, the Galileo's law of inertia and the Newton's law, the first law, which is also known as sometimes as the law of inertia, because Newton took it from Galileo. Galileo's law, whether it was originally conceived by Galileo or not, is doubtful. But since Europe was emerging out of the Dark Ages and Europeans started conquering the world over, they say that this is actually the beginning of the modern science. Anyway, the beginning of the modern science goes back to more than about 1400 years ago, when the great school, the Medina school in Medina, which was in Saudi Arabia at that time. Medina is the Prophet's city, and one of his great grandsons, he established a school over there, and that school lasted for many centuries. It's known as the Medina school, and one of the famous students of that school is the chemist. Okay, the chemist. I'm just forgetting the name. I'll talk about him in the due course of time. Okay, his name was. He was the one who came out with many chemicals and this and that, and he was an alchemist. Okay, I'm just missing that name. But I'll give it to you. No. It was, so yes, I remember now the name of the scientist, and the name in English is Gabber. But actually the name of the gentleman was Jabir bin Hayyan. Okay, he is supposed to be the father of modern chemistry, etc. Anyway, it doesn't matter at all which place. So, from Galileo, who gave the concept of inertia, and I will talk to you about that, inertia, which is the inherent mass in an object. When I say that, the mass in an object is 1 kilogram, then that is actually, it speaks about the inertia of the object. Then after that we discuss about Newton's laws. The first one was Galileo's law of inertia, which is a qualitative description of force. There is no quantitative description of force, and this was given by Newton in his studies of not only the earthly bodies, motion of earthly bodies, but also of the celestial objects. And he saw the beauty was that Newton could describe the modern mechanics, the dynamics of moving bodies, which we call the kinetics also, in the form of second law. And the third law of Newton is very well known to the masses all over the world, and I will discuss it very thoroughly, because as most of the people understand that to every action there is an equal and opposite reaction. Okay, anybody who has been taught this law, even in class 6, will remember at his or her deathbed. So then we discuss Newton's laws, first law, second law, and the third law. And in the course of time, that cannot be given in in the description of the second law, we need a concept which is called momentum. Momentum is, you know from your previous classes, is the product of mass and the velocity of a body. So linear momentum is mass into the linear velocity of the body, and the momentum, as I told you also before, that the momentum is equal to, and I use the term P was equal to the mass, which is a scalar quantity. It's almost invariant in the kind of mechanics that we do, the Newtonian mechanics. And momentum has hardly, in the languages Hindi or Urdu, we don't have a real translation. I know that in Urdu we call it samveg, in Hindi we call it samveg. We multiply the veg with sanghati and get the momentum. But in the Hindustani language, we do have a description of momentum, which I will tell you when we are discussing momentum, and from momentum we are able to derive, to obtain and tell you about the Newton's second law of motion. Then there is something called impulse, which I will define, okay? And then you know from the motion that we have been observing, there is friction, it's opposition to the motion, whether the body is sliding or the body is rolling, okay? And then about the frames of reference. If I have a frame of reference, for example, in the coordinate system that we have used in the previous discussions, x, y, z coordinates in space. So actually there are four variables: variable x, variable y, variable z. First of all, I will say that they are independent of each other. Why? Because x makes an angle of 90 degrees, I am repeating, y makes an angle of 90 degrees with the z-axis, and z makes an angle of 90 degrees, and resolved parts, as I told you, that if there is a vector like this, its resolved part in this direction will be equal to this value multiplied by cosine of the angle that is there. Okay? So they are independent of each other. The rectangular coordinates, the x, y, z coordinate system is x, is y, and this is z, three coordinate system that we have. They comprise a frame of reference where all these directions are any resolved parts in these directions are independent of each other, because the angle is 90 degrees and the cosine of 90 degrees is equal to 0. So there is no resolved part in those directions. Then the fourth variable in the space-time continuum is time, and time is independent of the location of a point in any of these axes or in any direction. So we have four independent things, but one of the things is that my frame of reference as it is can be mobile, can move, and it can move in space. But if there are two frames of reference and one frame of reference does not accelerate with respect to the other frame of reference, then that frame of reference is called inertial frame of reference. So they are not relatively, there is no acceleration. But if relatively there is an acceleration, then such frames of reference are called non-inertial. We will come and discuss that again. So, now there is word cause. As we understand, force is a physical cause which changes or tends to change the state of rest or of uniform motion or direction of the motion of any object. Okay, like I told you that in the uniformity of motion, there are two items. For a motion, for a velocity, there are two items. One is the magnitude and other is the direction. So we can change the magnitude without changing the direction. We can change the direction without changing the magnitude. Okay, we can change both magnitude and direction by making a physical cause. Okay. Now, in that sense, I have just mentioned here what is inertia. Inertia of an object is a property by virtue of which it opposes, it resists, okay, any change in its position of rest or of uniform motion. So that means it is an inherent property of the natural objects. It is a property associated with all natural objects that they oppose any change in their position, and the position could be the position of rest or of uniform motion. Now here I would like to introduce the force again. It is said that Galileo smashed the understanding of force as was propagated by Aristotle. But there is no record whether Aristotle deviated from any other previous understanding of force. But what he said was, and taking things into consideration, there are many things which are practical in the case of Aristotle, and I am no chamcha of Aristotle, but I keep him in esteem because anyway, the thing which he is blamed for is that Aristotle said that force is a must to bring a body in motion. Force is a must to cause a body to move. Listen again. It is the force which, even if the body is moving with constant velocity, he thought, and the people who followed him, they thought that a force is required. But this is what was questioned by Galileo, and maybe before that by other people. But let us give the credit to Galileo. Galileo explained, and so very beautifully, as to what was his law of inertia. Okay, so let us see as to what a force can do. The first thing is that we observe is the force can change the state of rest of an object. Here, this word rest needs discussion. But the second thing that it can do is, it can change the speed of a moving object That is, it can accelerate or retard. Retard means negative acceleration, which we also call deceleration, okay, of a moving object. The third thing is that it can change the direction of motion of an object, whether it is moving with constant velocity or speed, or is moving with changing velocity, okay, magnitude wise. Then there is another thing which the force can do. It can change the shape of an object, okay, and you have seen often that the shape of an object, and this is where I am just indicating that there is a thing which is called elasticity, plasticity, etc., that we can study later on. But let us discuss rest. In the frame of reference that we have, for example, this board is in a state of rest. In this room, for what I can see, for what you can see, it's not moving at all. Are we, now I question to you, are we in what we call, and I told you, inertial frame of reference, or we are in a inertial frame of reference? We are on the earth. The earth is moving, is rotating about its axis. In one day, the rotation takes place about its axis. We come back to the same position, and that is what causes the day and night, etc. The earth is moving around the sun with a tremendous speed in an elliptical orbit, which you can take. If the ellipticity is infinitesimally small, then of course we can take it as a circular orbit. The sun, along with its planets, it's also moving in the galaxy, and the galaxies are moving. So it is a very interesting system, but as we observe the things, we have to consider this state of rest. And it is the state of rest which fooled the ancestors, and they thought that it is essential to have a force to make an object move. But as I said, all these things the force can do. Let us go back to how Galileo saw, and he explained why in the state of rest or motion, there is no force which is required to maintain a uniform motion. I'll just tell you about the dialogues that were there in the Galileo's famous work on the two world systems. One was, of course, that of the dame, that is the church. The church is called a dame, which is evident from the nursery rhyme. Ba ba black sheep, have you any wool? Yes sir, 3 bags full. One for my master, one for the dame, one for the little boy who lives down the lane. This was the system, economic system, agrarian system, in which the produce of the farmers was divided in 3 parts. One part used to go to the king or the queen at that time, and one part was given to the dame, that is, it was given to the church, which had its own schools of teaching and learning, very nice scholars, very great people, but still they thought that the earth is the center of the universe. And later on it was found that no, in our system it is the sun which is the center of the thing, and which was established by Galileo, and the Galileo was then put in prison, etc., etc. So these are the things, the stories that you can read in the books. But what Galileo, he compared the two systems. One system was that of the church, and the other system was that of science, which had to be based on observations, etc. So in one of the famous arguments, it's very simple, this argument, in one of the famous arguments, he did some experiments with the inclined planes, and he took an inclined plane, a rigid inclined plane, and another plane going like this, okay, and then he gave the argument. He gave the argument that if there is a body, notwithstanding that there is friction, etc., but if a body is pushed up the plane, then he observed that the speed of the body will go on decreasing and decreasing until the body will come to a position of rest. Okay, so here he said that there is a negative acceleration. Negative acceleration. But if the same body is put on an inclined plane like this, and it is allowed to slide or roll or whatever on this plane, then he found that there is a positive acceleration. Positive acceleration. He could have simply said that there is a slope up the hill, there is a slope down the hill, but there is another plane which is neither up the hill nor down the hill. And if now an object is pushed like this, this will keep on moving and moving and moving. Of course, there should not be any friction. The friction will stop it. But now I am going to share with you a very simple argument. And the simple argument is that there is a negative acceleration when you push it up the hill. There is a positive acceleration when you push it down the hill, or you allow it to slide down the hill. But we all know, and from millennia, that from the scholars, maybe Indian, maybe Greek, maybe Arabs, maybe the Egyptians, maybe Mesopotamians, okay, wherever there was a civilization, Mohenjo-daro, Harappa, this, that, all kinds of civilizations, they knew one thing, and they knew that if we change from negative to positive, we have zero crossing. If we change from positive to negative, then there is a zero crossing. So something we define as positive and something we define as negative. So what happens? If we move from the positive to negative, are otherwise from negative to positive, then there is something which we have to define, and we have to define it as 0. So the acceleration in this case was negative up the hill, the acceleration down the hill was positive, but here was a situation when there was no slope. The slope here is equal to 0, because I'll just remind you, I defined to you the slope in the dy dx curve, and this was our delta y and this was our delta x. So I had this plane, this figure inclined to the x-axis by an angle theta, and the slope was defined as equal to delta y over delta x, which mathematically speaking is equal to tan of theta. If it is otherwise coming like this, then this tangent of theta, for example in this case, the tangent of theta will be negative. This case, the tangent of theta is more than 0. In this case, the tan theta or the slope, tan theta is less than 0. So here is a case like here, that the tangent theta is equal to 0, and this is what was argued by there are 3 characters in that book. One character which is very important is a simple man. Simple man with a thinking mind is a very important, has been a very important character, and when this thing was being explained and only 2 things were told, then that simple man, he asked people, wait. You mean to say that if it is not up the hill, it is not down the hill, it is in a plane like this, which is horizontal, then what will happen? Do you think that the body will keep on moving? Yes, and yes. And that is why we define that the first law, or the Galileo's law of inertia, goes like this: every body continues in its state of rest or of uniform motion unless impressed by an external force. Now look here, what did Galileo say? What was the argument? So I was saying that every body continues in its state of rest or of uniform motion unless impressed by an external force. Looks very interesting. Unless impressed by an external force. What does it mean? It is the external force which changes the state of rest. It is the external force which changes the state of uniform motion. Whether it is increasing or decreasing the speed of the motion, uniform motion, or is producing a kind of a deviation in its path by changing the direction of motion. What is the important thing? The most important aspect is that what was understood before Galileo, that force is required only to move an object. Now with the Galileo's argument, we can see that force is the agency, the cause, the requirement to change the motion, to change the uniform motion or the position of rest of a body. So force is an agent of change, not only the agent of movement. So uniform motion can occur without a force. because it is not accelerated. And in the laws of motion that we discuss, we find that force is very intimately related with the change, the kinematical relation, which is acceleration, and also the dynamic relation, the rate of change of momentum. Okay, or like we state that force is proportional to the acceleration and is in the direction of acceleration. Also, the force is proportional to the rate of change of momentum, and we derive those things, we discuss those things in the next lecture. So I hope that you have enjoyed the things, and of course we are indebted to people like Galileo, Newton, and many other sages in India and Greece and many other places for centuries, for millennia, who have helped us evolve these concepts, so life is easier for us. Okay.